Imagine you're the leader of a country being invaded by spies. These spies plan to infiltrate and hijack your country's resources so they can proliferate and invade other territories. Fortunately, these spies have unsuccessfully invaded in the past, and you now have a record of who they are and how they attack. Now, you don't want to be invaded, so once you find out that there are spies among us, you give pictures of what the spies look like to some of your subjects and recruit them to identify them undercover. Once they've been identified, the undercover subject eliminates the threat and your country is saved. This is essentially how the immune system of bacteria or prokaryotes work to defend against viruses or phages, who attack similarly as the spies of your beloved country. Phages attack by injecting their DNA into the bacteria, so it can be read and processed by the bacteria's cellular machinery to create more phages that then go on to infect and exploit other bacteria and their cellular machineries. Now, this is all very bad for the bacteria. But the good news is, if you know what the enemy looks like and can recognize their strategy, it can be easy to identify them and prevent them from ruining your nation. But how do the bacteria do that? How do they keep a record of past invaders so they can identify and eliminate phages from hijacking them? Enter CRISPR. Like all objects, pictures need a place to be stored so they can be appropriately used in the future. Pictures of your invading spies go in your royal palace library. Pictures of the bacteria's invading DNA go into their genome. For reference, here's how the bacteria's genome breaks down. When researchers were studying bacteria DNA in the late 1900s, they were confused as to why there appeared to be clusters of short, repeating identical genetic codes, or simply repeats. What was interesting about these repeats were that they were palindromic and read the same from left to right. Notice how these base pairs are complementary to each other. The repeats were regularly interspaced by unrelated, seemingly random short sequences, or spacers. Later it was found out that these spacer sequences matched up with the DNA of phages. It was concluded that these spacers in the bacteria's genome were the pictures of past invasions from phages, and were embedded in these clustered, regularly interspaced, short palindromic repeats, or CRISPR. This is how the bacteria store records of previous attacks against the cell. It's important to know that the genome is the original database for all the plans in the bacteria's life that will be used to make specific structures in the cell for different cellular functions whenever it realizes it needs them. It is not something that should be changed lightly. How are bacteria able to do this then naturally as an evolutionary feat? Join me next time where we uncover some of these mysteries. Take care now. Thank you for watching.